Hi students. So today we bring lecture 44 of the course, and today I'm going to talk about airplane takeoff performance. So this lecture is going to let you calculate the distance which the aircraft has to taxi before it lifts off, and this is also a requirement if you want to calculate the length of the runway. So at the end of the video I'm going to discuss about the FAR requirements in terms of the design of the runway and how long the length should be for the airstrip. I'm Dr. Ranjan Ganguly. So let's start looking at a typical runway. So let's say the aircraft starts at this point here, and at this point of course time is 0 and velocity is 0, and then it taxis along this particular length, and then at a certain point at a distance SLO it lifts off from the airstrip. So essentially the lift off would mean that both the front wheel and the back wheel have departed from this landing strip, and beyond that the aircraft is actually flying in air. So we can call this distance as LO as the ground roll or lift-off distance. So LO here can stand for lift-off, and essentially this lets you calculate to some extent the runway length which has to be there. This is the running length along the runway. Now at the end of the video, we'll discuss some FAR guidelines which also stipulates that the airplane should actually be able to cross a certain height before it can be safely said that it has exited from the system. So that's going to somewhat increase this length as LO, but right now let's just try to calculate this length as LO. So to do that, we are going to look at the forces which act on the aircraft when it is trying to take off. So this is the aircraft which is on the runway, and you can see here that the different forces which are acting on it of course depend on the gravity. So for example, you have the weight, and because you have a velocity coming from the front, you also have the lift and drag which are perpendicular and parallel to the velocity respectively. You also have the thrust in the forward direction. Now there is a new force here, and that's the force R. This force is present because of the rolling friction. So you will recall from physics that this rolling friction is going to be mu R into W minus L. So this is the reaction caused by the rolling friction, and mu R is typically a value such as 0.02 if you have a smooth paved surface, which is typical of most runways, but you may even be taking off from a grass field, in which case the mu R coefficient is going to be something like zero point 0.1. Now W minus L is the net normal force on the ground, so it's actually the weight minus the lift. So that's the complete downward force which acts there, and this reaction R is proportional to W minus L. So we can use these forces to get the takeoff equation of motion, which I have written here. So the force would be thrust minus drag minus R. So this would be thrust minus drag minus mu R W minus L, because do recall that R is mu R into W minus L. So because of this presence of R, the lift also enters into the picture here, and this total force according to Newton's law is going to be m dv by dt, where m is the mass of the airplane, v is the velocity, and t is the time. Now essentially if you had the variation of all these parameters, for example thrust, drag, weight and lift with respect to time, then you could integrate this using numerical integration. It would essentially become a differential equation solution problem with certain initial conditions and so on. But we are going to today derive a closed form solution for this, which is going to give us a good approximate results in terms of the length which the aircraft is going to travel through. So let's write this equation once again, and what we are going to do is we are going to simplify various aspects. So you can clearly see here that dv by dt is a function of thrust, drag, weight and lift, because R is actually proportional to weight and lift. So these are the four parameters here, and we know that lift and drag are going to vary considerably because of velocity, but thrust and weight are somewhat constants. They do have a small amount of variation, but relative to lift and drag, that variation is much less. So we can almost assume that thrust and weight are constant. Now the equation for lift is what we know from our previous studies of the subject, that is half rho v square SCL, where rho is the density, v is the velocity, S is the area of the wing, and CL is the lift coefficient. But in the case of drag, we have CD0 and we have one more factor here. And this factor is something which is coming from the proximity of the ground. So because you are flying very near the ground here, you are actually running on the ground. What happens is that the drag is going to be somewhat different, and this is a part of the drag you are going to have to be considered. So this phenomena essentially comes from the ground effect. So this is the effect of the ground. Now in the case where you were not near the ground, this phi of course would be 1. This would be simply the drag polar. But because of the presence of the ground, phi is less than 1. So what happens is that induced drag decreases near the ground, and this happens because the tip vortices which are shed from the wingtip, their strength is reduced. So therefore you find that the induced drag is less near the ground. Now this is a very important effect in the aerospace systems. You will see some vehicles actually have been designed, for example, which typically fly across seas, which fly very close to the sea, and therefore what happens in those cases is the induced drag effect is brought down. You'll also see many birds tend to fly very close to the water surface. Again, this will help them reduce the induced drag. So we are going to use a certain estimate of this value phi. So phi has been shown to be this particular equation here. So this is derived from some theoretical background. So we will say phi is 16 h by b square divided by 1 plus 16 h by b square, where h is the height of the wing above the ground and b is the wingspan. So these factors we are going to consider, and in the next slide I'm going to try to plot this equation. So before that, let us just take a look at the Newton's second law of motion, and this is going to become handy in the case of calculations for this particular SLO length. And why it's going to become handy is we are going to assume constant force. So let's start with the equation for Newton law, which we all know. F is mass into acceleration, that is mass into dv by dt. So I can write dv as F by m dt. I can integrate dv from 0 to v, and if I assume constant force, I can keep m out here or keep F by m out here and integrate dt from 0 to t. So this integral can be calculated, and I get v is F by mt or t is Vm by F. Now if you look carefully at this derivation, we have made two assumptions. One is that the force F is constant, and also the fact that at the start of this process the velocity is 0 and at the end the velocity is v, and also time is 0 and at the end the time is t. So these are essentially the bounds of the definite integral. So from that equation we can also calculate the distance. So remember from basic physics, ts is v dt, and therefore I can write this as F by m t dt. Now using this particular equation, I can write the ds value integrated from 0 to s is this equation here. So all I did is integrate the equation on top. Again, I assume constant force here, and so I get S is F by m t square by 2 or F by 2m, and this becomes Vm by F, the whole thing square. So that's essentially the time being squared here, and this gives us V square m by 2F. So this is the formula for the distance traveled from time 0 to time t. So that's the distance from 0 to s. Now of course we can look at this formula very carefully because this is something which we are going to use later. The fact that S is V square m by 2F, and we are going to try to calculate the force F, which is constant when it acts on the aircraft. Now, before we do so, just one fact to consider about the ground effect. The drag in the presence of ground effect was given by this equation. And so I mentioned that phi is given by this formula, and here I have plotted this value of phi. So you can see this is the plot of phi with respect to h by b. And as you can see that as h by b becomes larger and larger, for example, once it crosses 1.5 and so on, the value of phi becomes close to 1. So these are the regions where the typical drag polar formula applies. And what happens is that when you are close to ground, for example, you can look at these regions like zero point 0.2, zero point 0.4, zero point 0.6 and so on. In this region, the value of phi is much less than 1. It can be as low as zero point 0.2, for example. So the induced drag is going to be certainly lower in that particular regime. So you need to consider this phi when you are looking at any kind of drag calculation when you are close to ground and you are encountering the effect of ground. So now we are going to plot the different forces and see how we can get a constant value of the force. So let's start with each of these forces. Let's start with lift and drag first. So what I have done here, I have plotted the forces as they change from S equal to 0 to S equal to SLO. So do recall the aircraft is starting from the point S equal to 0 and it's taxiing around this point, and at S equal to SLO it is lifting off. So what will happen is that the velocity is going to keep increasing, and therefore as the velocity increases these forces are going to increase. Now from this formula we know that S is proportional to V square. Therefore the lift and drag are directly proportional to S, or the distance. So I can essentially put these two forces as straight lines because they are directly proportional to S here. So this gives me these two forces here, and of course the aircraft is designed such that the lift is the target, and so the lift essentially grows much more faster than the drag because we have an airfoil section, we don't have a blunt body, and therefore the lift is more than the drag. So these two are the starting forces which we get. Now let's look at the next two forces, and these are weight and thrust. And like I mentioned before, these do not change much. For example, the weight of course remains constant and the thrust changes slightly if we assume it's a jet engine, but it's more or less constant in this particular range. So now we have four forces here. We have lift, drag, thrust and weight. Of course, you'll realize that at the point when you are at liftoff, lift is equal to weight, and therefore the lift line meets the weight line here. So this point, these two are going to touch or intersect. Now let's look at the normal force. So do recollect that the normal force is given by mu r W minus L. So here you can see that when you start, L is going to be equal to 0, and therefore this is going to be simply mu r into W. So that's the value where you start the normal force, and then the normal force keeps decreasing, and at the point of liftoff weight becomes equal to L, so R is going to become 0. So this is going to give us the normal force line in the graph. So now we have all these primary graphs. We can calculate some of the graphs which come from the forces we have discussed. So let's start looking at D plus R. So D plus R is the drag plus the R force. So you can clearly see here drag is coming from 0, and here R was this value here. So D plus R starts from this point, and at the end again R becomes 0 and there's only drag. So this dotted black line, this is the D plus R force. And now what we do is we look at the thrust value here, and we can now go back to our equation, and we know that we want to calculate T minus R. So that's equivalent to T minus D plus R in brackets. We know D plus R, we know T. So essentially this brown line which indicates T, and the d plus r line here, we want to get the distance between these two lines here. That's the t minus d plus r distance which we need to get. So that's the force which is represented by this value F, and that's also going to be equal to m dv by dt. Of course, we see that this force is not completely constant, but it's not changing too much. So what we are going to do is we are going to take an average or mean value of this force somewhere. So let's again go back to our starting equation of motion for takeoff. This was our equation of motion here. M dv by dt is t minus mu r w minus L. And what we are going to do is we are going to say there is an F effective force, which is this force. This is the T minus D plus R component. And we are going to say that there is going to be an average value of this particular component D plus R. And this entire thing T minus this component is going to be a constant value. So if we were able to get this constant value, then we can use the equations we derived before. So we can use S is V square M by 2F, and we can get this equation here for SLO. So here what we have done is that we are looking at liftoff. So we put VLO here. V is replaced by VLO. Mass is replaced by weight divided by gravity. And then the force is replaced by this force here, the F effective force, which we obtained previously. And like I mentioned before, it is an average force, so we can use this formula here. Now, the V liftoff typically takes place at something higher than stall, so 1.2 into V stall can be taken as V liftoff, which is 1.2 times root 2W by rho infinity S CLmax. And then using this formula, we can get SLO is this equation here. So what we have done is just taken this and substituted for VLO in this equation, giving us this equation here. Now, of course, most of the parameters in this equation are going to be known. So let's look further at that. So just rewriting this equation, we can see here clearly that we would require to get an average force value here. And what is done is that the value at zero point 0.7 VLO can be used as the value for this particular quantity, that is T plus mu r W minus L at zero point 0.7 VLO can be used. Now we can further simplify the equation to get some physics out of this model. So again, this is essentially a math model. Let's assume that T is much greater than D plus R during takeoff. And this is typically true for most engines because the aircraft still has a pretty low velocity. And so thrust is going to be much greater. So in that case, in this equation here in the denominator, I can simply only keep the T term. So that's what I have done here. We have just discarded this term to simplify this and look at the physics of the problem. Now looking at this term or equation for SLO, I can clearly see that the liftoff distance is proportional to weight squared. So it is extremely proportional to the weight of the aircraft. So if you have heavy aircraft such as the Airbus A380, it's going to take a long runway length compared to a aircraft which is much lighter, and so on. Also, we see that SLO is directly proportional to 1 by rho infinity or 1 by density, and to some extent thrust is also slightly proportional to density. So from this equation we can see that on hot days you would have more SLO because your density would be low, so SLO would go up. Similarly, airports which are high, more runway length is going to be needed because high airports are also going to have low density of air. Recall the standard atmosphere. And also we see there is one positive news here is that CLmax can be increased by high lift devices. So for example, here CLmax is in the denominator. So if I were to increase CLmax using flaps and slats, then I could actually send the SLO down. So that's going to benefit me because the taxi length is going to decrease. So this is something you see happening in most aircraft, is that When they are taking off, the pilot will deploy all the lifting surfaces, and if you observe the wing, you are going to see all the lifting surfaces go up and go out, and they are going to increase the CLmax value. Now there is certain extra requirement given by the FAR or the Federal Aviation requirement, and this is that the total takeoff distance for a jet powered civil transport is SLO plus distance on the ground to clear 50 feet. So essentially you take this distance SLO, which we have calculated, and you add a certain amount of distance, which I have shown in this green line here, so that the aircraft can clear this 35 feet length height which is out there. Now if you are looking for all remaining airplanes, then the requirement is that it should be SLO plus distance on the ground to clear 50 feet. So here I have shown, for example, a propeller type of aircraft. So you are starting at velocity 0, you are doing lift off here, and then this guy must be able to clear this 50 feet height. So essentially when you're calculating the takeoff distance, you have to take this SLO and add this particular distance here. So to summarize, today we derive this equation, which is essentially the math model for takeoff, and it essentially gives us the length as far as the airstrip should be at a minimum level for the aircraft to lift off, and we see that it's very much proportional to weight, so it's directly proportional to weight square. So weight is something which has a huge impact in terms of the runway length. It's also inversely proportional to the density. So if the density is low, then the SLO goes up, and also there are different factors such as CLmax, which can help you because you can control CLmax through high lift devices. Beside that, all these other factors are also there. For example, the thrust, the drag, and also you want to keep mu r as small as possible. So the runways are designed such that the rolling friction is as low as possible. So you don't want this mu r value to be high. So that was the lecture about the takeoff performance. So takeoff of course is very important. Previously we discussed all the things about endurance and range in the cruise flight situation, but of course you need to take off and you need to land, and this is a very important part of the airport infrastructure and the aerospace infrastructure which is there, that is the building of runways and so on. And the formulas we derive today, it does give you some simple way in which you can calculate the takeoff distance for an aircraft, and that can be helpful in any kind of design as far as runways are concerned. Of course, if you want to get more accurate numbers, you will have to resort to numerical integration and get better values for the forces as they vary as the aircraft taxis on the runway. So I'll end this video here and I will see you in a video sometime soon. See you then.